Well, good morning, ladies and gents, and thank you, Professor Rosen, for inviting me. I'm really delighted to be here, and it's a pleasure. I'd like to thank the organizing committee for extending this invitation to me. We really enjoyed the hospitality, the Bulgarian hospitality. I look forward to this. I don't have any conflict of interest to declare. I come from Queen Mary University of London, which is ranked 14th in the world in research output and 7th in UK. We have 9 Nobel Prize winners from my university, and St. Bartholomew's Hospital, where I'm based, is 900 years old. So it's a very, very historic place. I'm an upper GI surgeon, and I'm passionate about technology and non-technical skill. So I'm not here to talk about esophagectomy, but see what we can learn from AI and how AI is shaping surgery in future. By surgical analytics, I mean computational or mathematical understanding of surgery. Yes, we are moving forward now. So that's an aerial view of London, and the red arrow is pointing towards the area just behind St. Paul's Cathedral, where my department is based. I've been there for over 2 decades, focusing on technology-enhanced education and training the next generation of surgeons in robotic and laparoscopic skills, including research skills. I'm also a global surgeon, and I operate through this Society of Surgical Simulation, which I founded. My global surgical work, my team has been going to Gaza, and we've set up a minimal access training center in Gaza, but that was before the war, and now you can see the state of the hospital. We are planning to go back to Gaza for capacity building and training. Currently, I'm doing a lot of work in Africa with the College of East, Central, and South Africa and West African College of Surgeons. The 2 colleges cover a geographic area of 33 countries. I've established this laparoscopic training curriculum, which is going to be embedded in the residency program in Africa. So as I was saying, pixels only matter, and for the first time in the history, we're able to convert pixels into insights, and those insights into prediction, and prediction into performance. We should think of AI not as something that will replace surgeons or for automation. AI can extend surgeons' mind, and what I'm talking about, referring to, is cognitive augmentation. There's a lot of research emerging now on this, but it is early stage research, pilot studies showing feasibility of how AI can influence it. The data is crude and currently not clinically usable. However, in fields like radiology, pathology, where you have good data from images of slides and scan, it's showing that AI can provide predictable outcome and actionable outcome. So let's look at what's happening in laparoscopic and robotic surgery. This is an example of surgical data management platform, CSAT. Can we have volume, please?
That provides consistent and objective expert feedback and clinical analytics designed to improve surgical proficiency. With CSATs, you can efficiently capture and store your surgical videos for future review, reflection, and learning. Also offers feedback, insights, and analytics related to a surgeon's skills and technique. View a personalized and private dashboard. Track your performance. Receive unbiased feedback from expert surgeons within your specialty, and view in-depth analytics on technical skills.
All the big companies are engaged in surgical data analytics. This is another example from Medtronic's DS1 platform that I personally use as well. This is for post-match analysis, I call it, to reflect on the performance and for training and education purpose. Similarly, in robotic surgery, the Da Vinci Intuitive Surgical Platform collects performance data from robotic surgeons, from robotic surgery. And surgeons in the hospital can access this data through my intuitive analytic platform. It gives us insight on efficiencies and inefficiencies in the procedure, helps benchmarking techniques, and hospitals are going to use this data for standardizing best practice and identifying training needs. However, that's all well said, but the reality is very, very different. Let's all go into the operating theater, and what do we find? Two surgeons can do the same operation with the same instrument on the same day, but yet have a different outcome. And why is that? It's because historically, surgery relies on surgeon's hand, which is motor skills, my eyes, which is sort of pattern recognition, and experience, which is cognitive skill. But all that is just coming from one source, which is one brain, one person, one dimension. I call it thinking in one dimension. Surgery has always been visual, but until recently, we had no way of learning from what we see. We've seen some excellent videos today, and we are learning from that, but how do we acquire skill and put it in practice in our operating theater? We can all agree what makes an expert surgeon is somebody who has standardized technique and skill, reproducible technique, something that he or she can make it look very, very simple, no matter how complex it is. Expert level decision making is combination of technical and cognitive skills. And studies have shown that only 65% of us are visual learners. So even though we watch, we don't really learn. And you can see in this video a simple procedure and how mistakes are made. And we keep repeating these mistakes again and again. Surgical videos are the cornerstone of AI, and it gives a host of information. In this slide, what you see is computational breakdown of laparoscopic Roux-en-Y gastric bypass operation. Each row represents one surgeon, and each column represents a step of the operation as you go from port incision to port closure. You can see this colorful chart. It's not uniform. This represents the variation in practice. It's not standardization, and we've all heard that how you can have better outcome if you standardize technique. Yeah. I like looking at other specialty and other fields. Look at this Formula One telemetry data of the top 3 drivers in different circuits and different corners in range, and see how consistent the performance is. Compare that with the surgical performance. I call it cognitive bottleneck. This is the human limitation problem that AI can help us with. How do we learn and store? As humans, it's only subjective from experience. And we know the performance of every surgeon declines as you get older. But AI, it's objective, it is statistical, it's mathematical. However, today, AI is not as accurate as we would like it to be. The accuracy of AI is in the region of 90%. We want it to be close to 100%. Procedure-specific accuracy of AI is still in the region of 90%, whether you look at upper GI cholecystectomy, hernia, liver resections, etc. So it's still not good enough. The reason it's not good enough is we don't have enough data, we don't capture data, and we don't use it for learning. There are factors that influence error rates for AI. It's the surgical complexity, adverse events, bleeding, and data from two-dimensional video. Most of the laparoscopic surgical videos are from two-dimensional, and one of the biggest factors is lack of standardization. So AI cannot learn unless we standardize this. However, with robotic surgery, we are starting to see higher precision and lower error rates with AI. The reason is obvious, because the vision is three-dimensional, magnified vision. The platform is already data-rich with a lot of instrument metrics captured by the robotic system. And the robotic instruments and the procedure that are done robotically for some reason are far more standardized compared to laparoscopic instruments. Now, on top of that, you throw in the 3D technology, the 3D insight that you can get from either 3D CT scan reconstruction or augmented reality overlay in any form of surgery, along with surgical planning, 3D modeling. All this makes it sort of very, very data-rich environment, the future operating theater. So, however, pixels only matter if they improve how surgeons view things. The 3D system and the 3D knowledge often improves accuracy because they change mental presentation. of the anatomy and of the movement of the surgical instruments. Yeah. And that translates into faster skill acquisition, as we have just heard, in the liver surgery, reduces fatigue and a safer decision-making in complex environment. So should the role of surgeon be a technician or a decision maker? I would say the role should be to move away from unidimensional thinking and reduce the cognitive load intraoperatively when we do complex tasks. Yeah. I'm sure you have all heard how women are good at multitasking and men are not. And doing an operation is not a single task, it's a multitasking operation. And hence, if you can reduce the load, it might improve the performance. What can we learn from aviation and military in reducing cognitive load and crew resource management? It shows that it frees up your bandwidth and allows you to think differently, and that improves your outcome. If you have iPhone, you will know what is Siri. But before Siri was born, it was called PAL, Personal Assistant That Learns. And where did PAL come from? You can guess, USA Defense Advanced Research Project Agency. PAL was designed to help military decision-making more effective and efficient. In 2007, it was bought by Apple and integrated into your mobile phone. Today, every flight that we fly has an autopilot system. Now, autopilot has not replaced the pilot. It extends their capabilities. It gathers data of hundreds of different parameters. The pilot remains the captain, but the system acts as a co-pilot and allows pilot to execute. Autopilot function is not a single switch. It's a whole instrument panel, and it changes depending on the flight path. That's a list of data that is captured by the autopilot when the pilot is still in command. Similarly, when we look at other industry, professional front-end video analysis in sports, every sport, we watch this day in and day out on our television monitor, how you get instant reflection and feedback on what the team should have done or should not have done. We don't do this enough in surgical practice. Today, the surgical video analysis is not as good as we want it to be. Therefore, the data inside is not helping us with decision making. We are at the right of the graph, and what you see over there is a paper that was recently published in British Journal of Surgery, just confirming that AI is in its infancy, and however, it's showing promising results here. Apart from not having enough data for AI, another problem that we can use to facilitate AI-based decision-making, if we fast forward another 50 years, what if you could get data not just from one source? At the moment, you got data from just one source, which is the video. What if you could get data from the surgeon himself or herself? And the surgeon is brain, eye, and the hands. So how do we decode surgeon's brain, eye, and the hands using neuroscience and neurosurgery? It is possible, and we are seeing emerging research capturing data from the brain using functional MRI machines, EEG, these are non-invasive tools, EMG, again, non-invasive, and there are invasive procedures as well for capturing data. So what can neuroscience do with co-adaptation? It's called co-adaptation.
Science. This concept is known as co-adaptation. And what that means to all of us is that by combining machine learning with neuroscience, this future interface will work with each user to adapt to their unique differences in physiology, sizes, preferences, and expectations. Here, you can see two people playing an arcade game with EMG. They're both using the same gesture, but because no two people are exactly alike, they do it in slightly different ways. The neural interface continuously gets better over time at understanding each person. The potential for co-adaptation extends beyond normal gestures into some truly novel territory.
Here, the algorithm is learning in real time how to respond to the EMG signals the person is sending with only the slightest of hand movements. The system is recognizing the actions the person has decided to perform by decoding those signals at their wrist and translating them into digital commands. And now, the person is able to communicate their intended actions to the computer with almost no hand movement. This is a genuine transformation in the way we interact with the digital world.
Science.
This is old news. AI can read your thoughts and turn them into words and images. If I show you this photo of that lady and scan your brain and feed the data of just the MRI into the AI, I get this output. So this is where we are with the data analysis with AI from just one photo. The future operating room is likely to look different. Currently, if you look at PubMed, publication on brain-computer interface is rising. There's more and more neuroscience research on brain-computer interface. The components of future operating theater will be surgeon, AI, robotics, 3D imaging, and analytics. It may look like this, but currently it's looking more like the cockpit of an aircraft. AI gives us the ability to convert pixels into insight, insight into prediction, and prediction into performance, not to replace surgeons, but to create something new. It is for the next generation to decide. The real question is whether surgeon will lead this transformation or be led by this. Thank you very much for listening.